In this video, I will talk about multiple regression model in R. Before you watch this video, please make sure that you have watched my other video called Multiple Regression Model. I have opened up the R script here for Multiple Regression Model in R, and I have already downloaded the data that is needed, and I have pointed out R to where I put this data sets on my directory. So this is needed in order to run the program. And then I select it and run this whole program. And this is the output that we see in the console window. The topics that I will talk today about are how to do multiple regression model and how to interpret the coefficients, partialing out, goodness of fit, including R squared and adjusted R squared, perfect collinearity, multicollinearity using variance inflation factors, omitted variable bias, variance in misspecified models, and homoscedasticity and heteroscedasticity. So to start, you need to install these packages here. So this code here installs packages and verifies that they're up to date. And so here's the first thing that we're going to do today. Let's run a multiple regression model. So to do that, we would be using a data set with wage examples. So we also want to interpret the coefficients, see how the coefficients are different for simple versus multiple regression. So let's go ahead and read the data file wage1.csv. And here's the directory that I specified above where my file is located, or you need to provide a full path here. So we're going to read a CSV file and assign that into our data frame that we're going to call wage1. So now from this wage one, we will select the key variables that we would consider, which are wage, education, experience, and tenure. We would provide the first 10 observations, and then we would see the structure of the data, and then we would summarize the data using the stargazer function here. Okay, so here's how the data looks like when we run this code. The first 10 observations of the data, here we have wage measured in dollars, education in terms of number of years, experience in terms of number of years, and tenure with the company also in terms of number of years. So this is data for the first person or first observation, second observation or second person, and so forth. We just have the first 10 people listed here, the data for them. If we're looking at the structure of the data, we are going to see we have 526 observations and 4 variables. And again, these are the first few observations that we have here. Getting some summary statistics with Stargazer. Here we would see the mean for all these observations, including $5.89 of um, average wage, average education being 12 years, and then experience being 17 years, and tenure with the company being 5 years. Okay, so next let's run a simple regression. So here's how we're going to run a simple regression. We're going to use LM for linear model. Wage would be our dependent variable. Education would be our independent variable. So it's a simple regression because we have one independent variable. Comma wage one is the data set right here that we is our data frame, our data set. And so here we're going to run this regression and we're going to call the results model underscore simple, and then we're going to summarize these regression results here. And that's what we're going to see here. So this is the model that we run. We're summarizing it. Here, R gives us back the formula, and these are the coefficients. We're going to concentrate right here on the estimates, same as coefficients. So the way to interpret education is for each additional 1 year of education, we have $0.54 increase in wage. And this intercept, which typically is not interpreted, but it shows what would be the wage if we have education equals to 0. But again, and people in the data set do not have education equal to 0. So it's just a statistical construct. Okay, so again, this is how you interpret the coefficient on education, noticing that we only have one independent variable. So next, let's run a few multiple regression models. So the first one would be LM for linear model. We're going to regress education. I'm sorry, we're going to be regressing wage, which is our dependent variable, on education and experience, which are our independent variables coming from the wage one data set. And in this model, we're going to regress a wage on education, experience, and tenure. So we're going to have one extra independent variable. And then let's summarize the model multiple one right here and multiple two, and let's see the results. So here's the first model where we have education and experience as independent variables right here. And these are the coefficients on that. So the way to interpret this coefficient is if education increases by 1 year, we would have that wages increase by 0.64 dollars. So notice that this coefficient here is different than this coefficient here. So that would happen when you include extra variables in the data set. And later on, we would also talk about also omitted variables. When you omit variables that need to be in the model, that basically affects the coefficient of the variables that are remaining in the model. And the way you would interpret the coefficient on experience is that if experience increases by 1 year, then wage would increase by $0.07 or basically 7 cents, holding everything else constant. Now, that's very important that we do not also change other independent variables when we change experience by 1 year. So if we add another variable in the model, which is now we can add tenure, that's how the results are looking like. So now we have the coefficient on education changed a little bit again. This is the coefficient on experience, and now we have the coefficient on tenure as well. If we would like to simply only display the coefficients, we may do so as well. They're stored as the summary in the summary for this model. And so all we have to do is just pick up this model underscore multiple two and then use coefficients. And that would basically give us the coefficients here, only the coefficients and nothing else as far as the summary statistics from the regression output. Okay, so next let's do predicted values. And residuals for these regressions. So these commands are the same as we have in the simple regression. So how we're going to calculate that to get the predicted values, we're going to be using the summary for the model, which is model multiple 2. And again, this was that model multiple 2, which is the summary output for this regression model. Okay, so using fitted from this summary is what calls the fitted values or the predicted values. So that's why we call these wage hat. We're giving it this name to recognize that these are the fitted or the predicted values. Now, from the same regression output, we can also call the residuals, and let's call these U hat because that would be the residual from the regression. So now, once we have these two new uh, uh, variables defined, we are going to mutate the data set to also include them as well in wage one. And then now let's go ahead, use wage one, the data frame, we're going to select these three variables from it, wage hat, and u hat. Well, they're actually, this is the dependent variable. This is the predicted value or the fitted value of the dependent variable, and this u hat is actually the residuals for the regression. So let's summarize these three things that we have here. Uh, and let's show the first 10 observations. And using the stargazer, we are going to summarize these in a table. Okay, so that's what we're going to see here. So notice here wage, this is the actual dependent variable that we have. Wage hat is actually the predicted value for wage. So again, the way to calculate this one is if you pick all of the independent variables that we have from the model, and then you multiply the coefficient times each of the independent variable, and that's how you obtain these fitted values. And you had the residual. You calculate this by doing by subtracting uh, the actual wage minus the predicted wage, and you can see 3.10 minus 3.76 is this minus 0.66 that's listed here. So this minus that would be equal this residual and so forth. So as we're calculating the summary statistics, notice the mean. So wage, the mean of the wage is the same as before, as I showed you before, of course. But here wage hat also has exactly the same mean. And this is by design of how these um, fitted values are calculated. So notice here that you had the mean for that is 0. So, and the reason for that is that wage is equal to wage hat plus u hat. So because we have the mean of the u hat equals 0, then the mean of the wage has to equal to the mean of the wage hat. Okay, so next, let's consider an important concept here called partialing out. So this is used for educational purposes to understand how the coefficients can be interpreted. However, typically we would not be using this part as we're doing research. It's just important to our understanding about how we interpret coefficients. So to do that, um, let's uh, uh, we would show that coefficients beta 1 are the same in the first and last regression here after we do transformation. So here's the first regression. Wage equals beta 0, that's the intercept, plus beta 1 times education, plus beta 2 times experience, plus beta 3 times tenure, plus u. So this model would actually be the same as the model that we have here, the summary results model multiple 2. So let's go ahead and see how it looked like. And these are the coefficients that we have here. And so let's concentrate on trying to replicate this coefficient here on education using another method, using partialing out. So again, what this coefficient here means and how it's interpreted is that if education increases by 1 year, then wage would increase by $0.59, holding everything else constant. So this holding everything else constant is very important in a regression. So when we increase education by 1 year, we do not also increase these variables by any amount. Our intention is to hold them constant. Okay, so now let's regress education on experience and tenure. So what we're doing here effectively is that we're picking up the independent variable in the model, we're making it a dependent variable, and we're regressing it on all of the other independent variables. So again, now our independent variable is a dependent variable regressed on everything else. So here, that's why education is regressed on the other independent variables, and these alpha 0, alpha 2, and alpha 3 are just the new coefficients that we're going to get here. So these are the results that we have. So here Education is the dependent variable, and these are the new coefficients that we have. So notice now this is the relationship between experience and education and tenure and education. Okay, so now what we're going to do is we're going to predict residuals E hat. So to do that, we're going to call this model partial. So basically, this model partial is the results from this linear model regressing of education on experience and tenure. So we're going to be calling the residuals and we're going to be naming them as E hat. And we're going to use the mutate function to assign these residuals back into the data frame. And so now we're going to be regressing wage on this E hat, the residuals from that regression. So when we actually estimate this model, we would notice that the coefficient now on this E hat on the residuals is 0.59. So if you scroll back up, this is exactly the identical coefficient that we have up here. Let me just scroll back up. This is exactly the same coefficient that we've had right here in the model before that we regressed wage on education experience and tenure. Okay, so what effectively happened here is that when we regressed education on experience and tenure, when we picked up the residuals from this model, the residuals in this model E hat are the variation in education that is not predicted by experience and tenure. So that's only the variation in education that is left, not predicted by experience and tenure. And so when we put them back into the model for wage, we put these residuals. The coefficient on this variable, it only explains the variation in education not explained by experience and tenure. This is why this interpretation of each coefficient in a multiple regression model, when we say holding everything else constant, is important because, again, it shows the variation of how education affects wage, holding everything constant and accounting for the fact that experience and tenure are being held constant. So again, this is important to understand how to interpret the coefficients in a multiple regression. However, we would not, researchers do not use this approach in order to estimate the model and report the coefficients. We, of course, straight estimate the model and provide the coefficients that way. Okay, so next, let's talk about goodness of fit. And we're going to discuss two measures here, which are R squared and adjusted R squared. So the goodness of fit measures show the proportion of variation that is explained by the regression, and the rest would be due to error. So let's go ahead and run a simple regression model that has one regressor. Uh, so here we have this is the same as model simple from above. So let's look it up and see the summary for it. Okay, so this was the model for the simple regression model. So here we have wage regressed on education, and of course we're using the wage one data set. And these are the coefficients that we have as we discussed them before. Now, um, as part of the output, you can also see here, it's called multiple R squared. So this is the R squared for regression, and this is the adjusted R squared for a regression, also reported here. So in a simple regression, these two numbers are going to be the same, and then we will discuss how we can calculate this R squared, adjusted R squared in a multiple regression model. And if you would like to also check, particularly on the R squared and the adjusted R squared, we can call these elements of the summary output by using summary, and then we pick up the model that we have estimated here. And then we use $ r dot squared. So this is calling the element in this model underscore simple summary output. And so same here, we can also call adjusted R squared coming from this model simple regression output, and we can summarize this. So the way to interpret this point 16 is that 16% of the variation in the dependent variable wage is explained by the independent variables, in this case by education, and the rest is due to error. The rest could not be explained by the model that we used. Okay, so now let's go ahead and run a multiple regression model where we have 2 regressors and then where we have 3 regressors. Okay, so here we have 2 regressors. So we have wage regressed on education and experience. These are the coefficients here. And notice that we have multiple R squared. This is the R squared for the model reported here. And this is the adjusted R squared. So notice that in this case, we would have these numbers being a little bit different from each other, or a lot different from each other, as the case may be. So they each measure different things. So again, the way to interpret this is that 22% of the variation in the data in the dependent variable for wage is explained by the model, and the rest is due to error. So now here, if we run three the model with 3 independent variables, we can see this is the multiple R squared that we have of 0.30, and this is the adjusted R squared. So in this case, again, the adjusted R squared happens to be a little bit lower than the multiple R squared. So notice one thing that is happening here. As we're adding more and more variables, the R squared increases. So in the first model with 1 independent variable, we had an R square of 0.16. With 2 independent variables, we have an R square of 0.22, so again, higher than 0.16. And with 3 independent variables, we would have an R square of 0.30. So this will always be the case that as you add additional independent variables, the R square would improve, which means that the model can explain, or the new regressors that are being added can explain more of the variation in the dependent variable. And of course, that would be the case. It's going to pick up more of the variation in the data. However, what the adjusted R square is helping us to achieve here is that sometimes the additional regressors may not be very good, and so by adding them, it may increase the R square, but it may not increase it by a lot. And so it may not make sense after all to add this additional regressor. So what this adjusted R square is providing a correction to not add too many independent variables. So it's starting to penalize if you add too many independent variables to say that the model is better and better. So we do want a good fit of the model. And again, we're looking at an R square of above 0.25 at least to have a good model fit, but we don't want to add too many regressors to a regression, especially if they don't improve the R squared uh, uh, too much. Okay, so now let's go ahead and calculate these R squared and adjusted R squared manually. So again, you do not need to do this in practice because we simply would read the regression output, but just so that we learn how it's calculated. So here, let's pick up from the data frame wage one, $, we're going to pick up the wage variable, and we're going to call this a Y. From the model multiple 2, we are going to pick up the fitted or predicted value, we're going to call this y hat. And for the residuals, we're going to call these e hat. And so, okay, so now let's go ahead and calculate these. SSE here would be the sum of squares explained, or the sum of squares model. And so this will be the sum of this y hat minus the mean of y, and this would be squared. Then the sum of square for the residual, that would be the sum of the e hat squared. And then the sum of squares total would be the summation of the sum of squares explained and sum of squares residuals. Okay, so how to obtain the number of observations? The number of observations would be n obs. We would call this element coming from the regression output. So this would be n. And here we see n equals 526. And K would be the number of regressors or number of independent variables. So from this model multiple 2, this is the regression output for our model. $sign rank is picking up the rank of this model, but it includes an intercept or a constant. So it includes the constant as a regressor. So that's why we need to do -1 to just get the number of independent variables. And so let's see what is K. K is 3. So again, we had 3 independent variables, right? Education, experience, and tenure. And so now we're ready to calculate the R squared and adjusted R squared. So the way to do that is we're going to define the degrees of freedom for SSR, which would be n minus k minus 1. So we're going to calculate this, assign this as degrees of freedom for SSR, and then n minus 1 would be the degrees of freedom for SST. So the R squared would be SSE divided by SST. We would assign this as R squared. So let's see what R squared is. It's 0.30. And the adjusted R square, we're going to be using this formula here, which is 1 minus the SSR, the sum squared residuals, divided by its degrees of freedom, divided by the SST, the sum squares total, divided by its degrees of freedom. And this adjusted R square would be the number that we have here. So this again is how we can calculate the R squared and the adjusted R squared manually. Again, typically you would not need to do this by hand, like manually like this. You can just look at the regression output, but it's important to understand the formulas. So again, the reason why when we add many more variables, the adjusted R square may be going down, is that when this K increases very much here, this K here is with a minus sign, but it's within the denominator, and then it has a minus sign here. So we actually would have that basically we would be seeing lower and lower adjusted R square as we're getting more independent variables. So that's going to be like our correction factor. So as you're adding more independent variables, the adjusted R square may increase or decrease. You can use this as a criteria of whether or not to keep a new independent variable in the model. So if the adjusted R square increases, keep it. If the adjusted R squared decreases, do not include this variable in the model is one of the criterias that we can use. Okay, so now let me show you a different example, which is the CEO salary example, and show you here that we have R squared and adjusted R squared. So for this, what we're going to do is we're going to be calling a new data set which is the CEO cell 1.csv. We would be assigning this as the CEO cell 1 data frame here. So let's go ahead, select the variables that we're going to use. This is salary, log salary, ROE, return on equity, sales, and log of sales. So let's pick up the first 10 observations for this data set, and then let's see the structure of the data set and use Stargazer to summarize these variables in this data frame. Okay, so here are the first 10 observations. We have here salary, we have log salary, ROE sales, and log of sales. This is the structure of the data, 209 observations, 5 variables, and these are the mean here. So one very important thing to notice here is that when we go from the level of a variable into logs, you see how we are basically also would have a lot less in terms of variation in the data when we're going down, when we're transforming the data by using logs. So let's go ahead and estimate the 4 possibilities and transformations in the model, depending on whether or not we use logs for the dependent variable and logs for the independent variable. So the difference between these 4 models here is, here we have the linear form where we have salary is regressed on sales. Here for the linear log, we have salary regressed, but this time on log sales. Here we have the log linear where the log salary is regressed straight on sales. And here we have the log-log forms where both salary and sales are in log form. And so estimating this model, we can summarize these models, and then from this summary, we can pick the R squared element and the adjusted R squared element to just see what these are. So uh, if we go ahead and do that, these are again the different models, and you know we actually have these listed in the output. We didn't have to specifically also call for these elements, but it is just helpful to know how to call them if you need them in the future. So here, notice that we have R squared and adjusted R squared. We have a 0.01 here in the linear log model. We have the adjusted R squared being 0.4. And then for the log linear form, we have the adjusted R squared being 0.12, and here we have uh, 0.27, 0.28 for the log-log model. So again, when we're switching into logs for the dependent variable, we actually have less variation to explain. So we actually see here higher, we generally see higher R squared when we switch to the models here of logs for the dependent variable. And so using the adjusted R square criteria, we would conclude here that the log-log model has the highest adjusted R square. So basically it can explain most of the variation in the data. So if we are only using this criteria as a selection, we would be selecting the log-log model because we have the highest adjusted R square. And another thing that we can notice here is that SST, the sum of squares total, would be different for salary versus log salary. And again, this is because the sum of squares total, which is the difference between salary and salary hat, that one would have more variation than log salary minus log salary hat. Okay, moving on with the content. Next, let's talk about perfect collinearity. Perfect collinearity is when we have an exact linear relationship between variables. So this is actually very problematic when we have regression. So here, perfect collinearity example is when we have a variable that we can now define as male that is equal to 1 minus female. And so we would call that the variable male is perfectly collinear with the variable female. So let's switch back to the example, to the wage example. So this is a model that we can estimate that has no collinearity problems. So let's go ahead and regress wage. on education and female. Now, female is again a binary variable equal to 0 and 1. So basically, the female variable would be equal to 1 if the person is female and 0 if the person is male. And let's go ahead and summarize this model. And here's what we have here. So if we want to interpret the coefficient here, we would say that if the person is female, she would have $2.27 lower wage than males. And that's how we interpret this model. So now we can actually calculate a um, a variable male, which is the exact linear function of female, showing perfect collinearity. So let's define the variable male equals one minus female. And then let's basically use the mutate function to put it back in the data set. Okay, so now that we have this variable male defined here, let's go ahead and estimate a model for wage, but with male instead of female. So here everything else is the same, but instead of female, we're putting male in the equation. So notice how these results differ here, and we will talk about this later on. The coefficients here are the same except for the coefficient on male and female, which are opposite of each other. So here, if we have females are making $2.27 less than males, here we would say that males are making $2.27 more than females. So these results are opposite of each other. So we can include female or male in the model, but not both. Let's see what's going to happen if we try to run a regression that has both male and female in the model, which would be an example of perfect collinearity. So if we do that, what R is going to do is it will automatically drop one of the variables from the model, and it would give you exactly the same results as we had before, because it's not possible to estimate a model that has these variables perfectly collinear. And the reason for that is that you cannot change one variable uh, without by holding the other variable constant. If they're perfectly collinear to each other, if we change one of the variables, the other has to change. So this is why it's not possible to estimate model that has perfect collinearity in it. And so an alternative way is to actually run a regression with no constant option. So the way to do this here is we are going to use the model wage tilde, and here we're going to specify 0 for no constant. And so if we summarize this model, you see that very strangely, we do not have here an intercept anywhere in the model. So notice that we do not have this intercept here. So again, not many economists are doing this. So this is not very typical to use use no constant option to estimate a model when we have perfect linearity. The best way to do that is just to recognize that the model has perfect collinearity, and for you to actually drop this variable yourself, the variable that causes this problem. Okay, so now we talked about perfect collinearity, where there's an exact relationship between the variables. So let's switch and talk about multicollinearity, when regressors are highly correlated with each other but not perfectly. Okay, so here we would be using the variance inflation factor to check for multicollinearity. Okay. We would be using test scores example here. So we are going to be using this data set, and we are going to assign it into our data frame. And let's select these few variables here, and then show the structure of the data, then summarize it and provide the first 10 observations. So here's the structure of the data. We have 400 observations, 4 variables that we selected. This API is the test score for the student. We have average education, and then um, we have whether um, the parents have been to graduate school, and to whether or not they have completed college education. And this is their average education. So these are the variables that are candidates for being very high to have to be multicollinear with each other, because the average education of the parents is very likely correlated with whether or not they completed graduate school and whether or not they're college graduates. So these are the first the first 10 observations of the data here. And so let's check next. As I said here, the parents' average education is collinear with whether or not they completed graduate school or college. So let's first look at the correlation table. So we are going to be using this data frame that we define up here above. We are going to select all of the variables except for the test scores. So basically, we're selecting the other 3 variables. And then here, NA omit, we want to remove observations that have NA or missing, not available, or missing observations. And then core provides the correlation table here. Okay, so this is the correlation table that we have. And we can see again very high correlation between the average education of the parents and whether or not they completed graduate school and college. Uh, college. So again, we have an indication that this is problematic. So here we have a pairwise correlation. So basically, we're looking at correlation between just 2 variables in a model. Now, in order for us to calculate variance inflation factors, VIF, we need to run the regression and find these. And then our criteria is that if these variance inflation factors are greater than 10, we would drop the variable. So let's run the model here with test scores regressed on the average education, graduate school, and college graduate. And let's actually calculate these variance inflation factors. So these variance inflation factors would be right here. And so again, what we're seeing here is that this variance inflation factor on average education is above 10. So this variable is problematic, and it's causing multicollinearity in the model. And so let's go ahead and actually run a regression without the variable that has this high VIF. So if we run this model and we would be reporting the VIF, we would see that there's actually no problem with the VIF. And we can alternatively also run the model that um, with the other variables. So that's also possible to run the other model and avoid multicollinearity. So here we have that variance inflation factor is equal 1 by definition for simple regression, but the VIF function does not allow for a simple uh, to, does not provide VIFs for simple regression in this case. So again, this is how to resolve the problem of multicollinearity, running the model, checking the VIF for each of the variables here. Any variable that has a variance inflation factor above 10, we need to drop it from the model, and then re-estimate the model again, and then see that actually the VIF factors are okay and below 10 after we re-estimate the model. Okay, next let's talk about omitted variable bias. So omitted variable bias occurs when we have omitted variables, so variable that should be in the regression, but it's not in the regression. It's omitted because either we don't have data or we didn't include it in the model, and this would cause biased coefficients. So let's show that these coefficients are in fact biased. So for this wage 2 example, let's use the HTV dataset, then read it in, and let's select wage, education, and ability of a person. And then let's show the structure, summarize, and first few observations of the data. So here we have this many observations, 3 variables as far as wage, education, and this is the ability of the person, like how able a person is. Okay, so this is the summary statistics for the data, and this is how the first few observations look like. So now let's assume that the true model has education and ability. So here wage would include education and ability as the true model. So notice that here we would have beta 1 being the coefficient on education, beta 2 being the coefficient here on ability. So let's call this a model true, the regression output results by running a regression of wage on education and ability using this data. And let's summarize the model. So these are the model results that we see here. So here we have a coefficient on education right here. So this coefficient here shows that if this is the true model, that if education increases by 1 year, then wages would increase by $1.15. This is actually the coefficient that we have on ability. So basically this shows the relationship between ability and wage. So what this coefficient here shows us is that there is actually a relationship between ability and wage as well, and that this basically this variable needs to be included in the model. That is the true model. So let's go ahead and basically pick up the um, coefficient beta 1 that we have, and for that we're going to use coefficient from this model true. That's basically model true is how we call these results coming from this model. So let's pick up this coefficient on education, and then beta 2 we would pick up the coefficient from the model true on ability. So basically, I'm just assigning these beta 1 and beta 2 coefficients. So I'm saying to R, pick up the coefficient on education, call it beta 1, pick up the coefficient on ability, call it beta 2, and let's store these because we're going to need them later on. So again, notice the coefficient on education is it's 1.15, showing each additional year of education increases wages by $1.15. And this is the coefficient on ability. So now let's assume that we do not have data on ability. If that what and I'd like to know what would happen if we actually estimate a model that does not include the abilities, where ability would be a omitted variable. So before we do that, please note that there is actually a model between ability and education. So here, if we want to have a linear model of ability regressed on education, so this omitted variable is now, a variable that was an independent variable in the model before, now we're going to have this as dependent variable, and that's education was our original independent variable. So if we run this model and then summarize it, and then we pick up the coefficient from this model right here, and we on education, and we call delta 1. So again, we're estimating the model of ability on education, and we're picking up these delta 1 coefficient here. So when we do that, here is this model of ability on education, and this is the coefficient here, 0.55, the coefficient on education in the ability model. So we're going to also store this as a delta 1 coefficient. Okay, so the final model that we're going to consider here is a model where ability is the omitted variable. So what we're going to show here is that the coefficient on education is biased. Okay, and as we have done in the previous video here, we have that if education, I'm sorry, if ability is not available and it's omitted, because it's actually related to education, we can actually plug in this expression into this model here for ability and then open the parenthesis, and that's what we're going to find. So what you see here is that coefficient of education is biased. It's not beta 1 as it used to be here before, but it has beta 2 times delta 1 attached to it. So this beta 2 is the relationship between ability and wage, and this delta 1 here is the relationship between education and ability. So this is this bias that we see into the original coefficient when we actually miss ability. Um, Okay, so when we estimate this model, this is now the coefficient that we have. So we would wrongly interpret that if education increases by 1 year, wages would increase by $1.39. So we now see that we have overestimated the effect of education on wages because we don't have this ability in the data, uh, and we have not included it in the model, and therefore this education is trying to pick up some of the effect of ability. And so the reason why we have a positive bias of 24 cents, so the difference between this coefficient and the previous coefficient of $1.15 is 24 cents. The reason why we have this bias of 24 cents is that uh, we have the bias here is beta 2 times delta 1, and that is these 24 cents that we see here. And if we want to calculate again the bias coefficient, we need to sum up beta 1 plus beta 2 times delta 1. Basically, what we're trying to do is calculate this coefficient here that is biased, and we would get exactly this here 1.39. And so again, this is the problem with not including a relevant variable in the model. We are going to have an omitted variable bias, which means that the coefficients on the rest of the variables in the model would be biased. In this case, we see a positive bias because we also had a positive relationship uh, between ability and wage, and we also had a positive relationship between education and ability. So effectively, our coefficient was overestimated in this model. If we use the wage example here, we can discuss a different example that we have here for omitted variables. So let's say that the true model is wage regressed on education and experience. Then we can show that experience is related to education, and then show what would happen if we actually just have wage regressed on education. Okay, so the original model and the true model that we're assuming is the true model here would show that the coefficient on education is 0.64. Now, the relationship, and then we also see that experience has a positive relationship to wages. Now, if we estimate a model between experience and education, here we actually see that we have a negative relationship. So basically, when education is higher, experience is actually lower. Okay, and finally, here is the model where experience is omitted. And here we see that the coefficient on education is 0.54. Actually, that is now lower coefficient than before. And the reason why it's lower is because we now have the relationship between education and experience being negative, and therefore we have a negative bias here. Okay, next, let's talk about a variance in misspecified models. So, again, the biggest problem of omitted variables is that the model is misspecified, and then we have a possibly biased coefficient, which is a bad thing. But another thing that we need to consider is what happens to the variance in misspecified models. So let's consider the same example as the omitted variable bias that we have above. So we would be using the same data set and the true model with education and ability. So our true model would be wage regressed on education and ability here. And let's go ahead and summarize it again. So this is the original model, the true model that we have with both of these. And let's notice what is happening here with standard errors here of this model. And here, when we estimate the model where ability is omitted variable, we would get the coefficient here on education. So this would be the standard error for this coefficient, 0.10. And this coefficient here was, and I'm sorry, the standard error here was 0.12. So while this coefficient is the correct coefficient, and here we have a biased coefficient, one of actually the one thing that's also happening is the standard errors are lower. So this is actually a desirable thing for a coefficient to have lower standard errors. Um, Okay, the final thing that we would talk about today here is about homoscedasticity and heteroscedasticity. So homoscedasticity is when the variance of the error term will be constant for each x, and the heteroscedasticity is when the variance of the error term is not going to be constant for each x. So let's go back to the wage one data, and I wanted to show you the summary results first. So these are the summary results first. So in order for us to look at homoscedasticity, potential homoscedasticity or heteroscedasticity, what I would like to do here is plot the residuals, plotting the residuals here. So to do that, we would be plotting the residuals with the geom point. And here we would use ggplot. We would specify the data is wage one. Here we would have that X would be education. So the horizontal line here, we want education. We're specifying the theme. And here we would like to see on the vertical axis Y U hat. U hat again, if you scroll back up, was the residual from this regression again that we picked up from the summary model. And here we would be also including the intercept using red color to add a horizontal line, and we would be labeling the y-axis residuals. Okay, and these are basically this is the graph that we have here. So here we have plotted education on the horizontal line, and these residuals you had are plotted on the vertical line here. So one thing we're noticing here with these residuals is it seems to me, and this is zero, so they're centered around zero, but as we education increases, notice what happens to the residual, to the variance in these residuals. It seems, at least visually for now, that this variance is also increasing. So this perhaps would lead us to the conclusion that we have perhaps some heteroscedasticity present here. We can also do the same thing with experience, plot these residuals against the experience using ggplot. So let's go ahead and do that. And so what we're going to see here is that these residuals, you see how, well, it's always very difficult to interpret graphs with real data, but it seems that these residuals are kind of more along a band rather than increasing or their variance increasing as the independent variable increases. So at least here visually, we could think about whether or not the residuals are exhibiting constant variance as we go along the different values for the independent variables. So again, we would have more rigorous tests to establish heteroscedasticity later on, but this is the first graphical check on them. So that concludes this program.